We'll now move on to what's sometimes referred to as the no assumptions bound. It's called this because all we need to assume is that the potential outcomes are bounded. For example, if we know that y0 and y1 are between 0 and 1, then we know that all individual treatment effects must be less than or equal to 1. This is because we just take the maximum value of the outcome minus the minimum value of the outcome. 1 minus 0 equals 1. Similarly, we must know that all individual treatment effects must be greater than or equal to -1. This is because we just take the minimum value of the outcome minus the maximum value of the outcome. 0 minus 1 equals -1. Then, because all individual treatment effects must be between -1 and 1, we know that the average treatment effect must be between -1 and 1. So we can trivially get an interval of length 2. 1 minus -1 is 2. And the spoiler is that with the no assumptions bound, we can cut this interval length in half. Right, so this trivial interval length is twice as large as what we'll get without making any more assumptions when we get to the no assumptions bound. Rather than using 0 as the minimum potential outcome and 1 as the maximum potential outcome, we'll use A as the minimum and B as the maximum. This is the more general setting that we'll be working in throughout this whole section of the lecture. Then, just as in the more specific example above, this means that the individual treatment effects must be bounded between A minus B and B minus A, and the same for the average treatment effect. This gives us a trivial interval length limit of 2 times B minus A, from just subtracting the lower bound A minus B from the upper bound B minus A. And with the no assumptions bound, we'll be showing that we can cut this trivial length limit of 2 times B minus A in half. We'll get just B minus A as our interval length for the no assumptions bound. Before we can get to the no assumptions bound, we'll quickly derive what we will call the observational-counterfactual decomposition. This decomposition is really important because we'll be using it for all of the different bounds that we get in this part of the lecture. So we're going to start with the ATE here and try to decompose it into something that might be useful to us. As usual, the first thing we do is use linearity expectation. Then we break each of these terms up into 2 components each. This is the usual trick of conditioning on some variable and then marginalizing it out. Here we're conditioning on treatment. So for example, with the expected y1 potential outcome, we're conditioning on t here and here, and then marginalizing it out by multiplying by the marginal here, here, and then summing over them. And then it's the same for the expected potential outcome y0. Then we can turn this into this, where the first thing we've done is we've taken this expected y1 given t equals 1 and just changed it to the expected value of y given t equals 1. Here we used consistency to do this. And then the same thing here with the y0 potential outcome. We call this the observational-counterfactual decomposition because right here we have observational terms. These can be computed from just the observational distribution. And then here we have counterfactual terms. So the outcome that you would receive if you had t equals 1, given that you have t equals 0, is counterfactual. And then same with this term here. And this is the observational-counterfactual decomposition. We give it a box here, and we've just taken these p of t equals 1, and we've replaced them with pi. Similarly, p of t equals 0 will be 1 minus pi, and we'll be using pi throughout this section. This is the decomposition that we'll be starting with for all of the bounds in this bound section of the lecture. And the first one is the no assumptions bound. To get all of these bounds, we need to bound these counterfactual parts of the decomposition. That's because we can't compute them from the observational distribution. Okay, so the goal is to get an upper bound and a lower bound on the ATE here. And the first thing to notice is that we don't need to do anything with these observational quantities. We can just copy and paste them into our bounds because we can compute them from the observational distribution. Then we'll upper bound this counterfactual quantity here, Because the outcomes are upper bounded by b, we can just put b in there for the upper bound. Similarly, we need to upper bound this negative counterfactual quantity here. Because it's a negative quantity, we actually want to take the minimum outcome that we could have. So all the outcomes are lower bounded by a. So the minimum outcome we could have is a, which we plug in there. And then it's just the reverse reasoning for the lower bound. So we want to lower bound this counterfactual quantity. We do that by just taking the smallest number that the outcome could be, which is a. And then for this negative quantity here, we plug in b, the largest potential outcome that we could have, because it's a negative quantity. And that's our no assumptions bound. That's all there is to it. After we have the observational counterfactual decomposition, it's pretty simple. How big of an interval does this upper and lower bound give us? First, for comparison, recall the trivial interval that we got earlier in the lecture. The ATE must be between b minus a and a minus b, which gives us a trivial interval length of 2 times b minus a. And now here's the no assumptions bound from last slide. By just taking the upper bound and then subtracting the lower bound, we get this for the interval length. So this term cancels with this term because they're the same. Same with this term cancels with this term because they're the same. Then this one shows up here. Then this negative, because we're subtracting it, turns into a positive. Similarly, this term shows up here. This term, we're subtracting it, so it turns into a negative. And this interval length is just b minus a, which is half of the trivial length limit of 2 times b minus a. So without making any additional assumptions, we're able to cut in half the trivial ATE interval length that we saw earlier in the lecture. Now that we have the no assumptions bound, it might be worth plugging some numbers into it in a running example. And this specific running example will be something that we use throughout this whole part of the lecture. So in this example, the potential outcomes are bounded between 0 and 1. The probability of treatment is 0.3. The mean y in the treatment group is 0.9. And the mean y in the control group is 0.2. Here is the no assumptions bound again, so you can see what we're plugging these numbers into. And here are these numbers plugged into the no assumptions bound. If you do a bit of arithmetic here, you get this for the interval for our ATE. The ATE must be between negative 0.17 and 0.83. It's a bit unsatisfying that this interval contains 0, because ideally we would have an interval that is only on the positive side or only on the negative side. So then we know whether or not there is a causal effect. So if the interval contains 0, there might be 0 causal effect. And in addition, we would know that the causal effect is either positive or negative. It's either beneficial or detrimental. So you can actually work out that the no assumptions bound will always contain 0, no matter what example, what numbers you plug into it. And similarly, many of the bounds that we'll see soon also contain 0. We'll eventually see one towards the end of this section that doesn't contain 0. It ends up being only positive, telling us that under those assumptions, we know that the causal effect is beneficial. We've now reached the end of the no assumptions bound part of the lecture, so I'll leave you with these few questions. Go ahead and pause now and answer some or all of them.